All right, we're going to cover the last part of chapter 12. All right, this is where we had left off the other day. Make sure you've got some paper and periodic table and calculator with you when you're doing these. I know a few people have written and asked if they need to show me the notes they're taking. I don't need to see those. I hope you're taking them, but I don't need to see those. Just the vocab and the outline, when those are due, I need you to, make sure you're attaching those, getting your homework problems done. But I don't need to necessarily see these notes. But hopefully you're taking them, because obviously that should help you. Okay, that's the reason we do these. So the last time we were talking, we were going through these notes, right? We had talked about how to solve problems in which you're given some kind of unit at the beginning. So in this problem that we covered last, right, we started off with liters, and then the problem wanted us to figure out how many molecules that was, right? We had to go from liters of one substance to molecules of a different substance, and they gave us a balanced chemical equation. And so we said, okay, those are the kinds of problems where no matter what unit you're given, you have to change that to moles first, right? And then the moles of one substance to moles of another. So you had to use the mole ratio from the balanced equation. And then you had to change the moles of that second substance into whatever units they were asking for. So we're using a combination of the conversion factors we learned back in chapter 10, and we're using the mole ratios that we learned in this chapter to convert any unit to any other unit in a balanced equation. Now, here's the one other layer to this that we haven't introduced, and that's going to come here today, the last part of chapter 12. If you look at this problem that we had just done before, you notice that the original balanced equation says that there's 2 NO, right? So 2 moles of nitrogen monoxide plus 1 O2 plus 1 mole of oxygen would make 2 moles of NO2, 2 moles of nitrogen dioxide. Okay? So this tells us that if I take 2 moles of NO and I add 1 mole of O2 to it, I will make 2 moles of NO2. Right? That's my recipe. That's what it's saying that I should be able to do. Now, this problem here below it says that we have some NO, but it never mentions anything about the O2. And we didn't even blink an eye. We didn't even look at that at all. We just assumed there was O2 there, even though it didn't say so. Well, here lies in the problem. Of course, there must have been O2 there. They didn't have to tell you that. There was O2 there in some amount, some plenty amount, and we just assumed that we didn't have to worry about it. But that's not always going to be the case. You know in real life that if I ask you to do this actual chemical equation, so I wanted you to get some nitrogen monoxide out, and I wanted you to get some oxygen out, and I wanted you to mix the two together. Okay, let's say we were in a lab and we were able to do that. If I wanted you to do that, right, the amounts that we have of both of those are going to be important, not just the NO. I need to know how much of both I have to be able to figure this out. So that's what we're going to do here in this part of the chapter, right? We're going through and we're going to be talking about limiting reagents and then eventually percent yield, okay? So let me relate it back to like a recipe, because that's essentially what these balanced chemical equations are. So let's say we're making a recipe to make, I don't know, cookies. Doesn't really matter. So let's say the recipe calls for 1 cup of flour and 1 cup of sugar and blah, 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 and some other things, right? And so you go into your kitchen and you're looking for your flour and your sugar, and you notice that you only have 1/8 of a cup of flour, but you have an entire cup of sugar, right? So if you don't have a full cup of flour like the recipe says, could you still make cookies? Sure you could, right? You could. You still have some flour. But if you only have 1/8 of a cup of flour, and the original recipe says that you needed 1 cup, then obviously you're going to have to cut that recipe 8 times, right? It's going to have to be 1/8 of what you could have made originally. So you could still make cookies. It won't be nearly as many as you thought you were going to make, but you could still make them. But now you're not going to need all of that sugar anymore, right? Because the original recipe said 1 cup of flour for every 1 cup of sugar. So it's a 1-to-1 ratio. So if you only have 1/8 of a cup of flour, you're only going to need 1/8 of a cup of sugar also. So in other words, the flour is one of our reactants, and it's limiting how many of the product I can make, right? The sugar I have in excess, I have plenty of sugar. I could have made the whole recipe if all sugar was the only reason I had to make it with. But I needed the flour, and I only have 1/8 of a cup of flour. Therefore, flour is limiting how much I can make. So this is a concept that we use when we're talking about balanced equations too. Right? So the flour in this case would be the limiting reagent. Reagent is just another word for reactant, so that's fine. Right? It's just another word that we use sometime in place of reactant. But it is the one reactant that limits how much product that can be produced. Okay? The other reactant that I have plenty of is called the excess reagent or the excess reactant. So every time that I have a chemical equation that involves 2 or more reactants, I'm always going to have at least one of those reactants that's going to limit how much I can make. And that's really important. That's going to be the important reactant. Because once I run out of that reactant, the rest of the reactants don't matter anymore. Because I won't have any of that first reactant left over to continue the reaction with. So one of the jobs that we're going to have when we do problems like this is we're going to have to figure out which of the reactants is our limiting reactant. Which one's going to limit how much product we can make. Let's go back to that bicycle. Remember that bicycle example that we had a while back? We talked about if you had to, go to a bicycle factory and make bicycles, and you had a balanced equation, right? We had a way of making bicycles. How many wheels would it take? How many handlebars would it take? Let's say you're at the bicycle factory again, and you have 24 wheels, and you have 10 handlebars. And of course, you know in your head, you need 2 wheels for every bicycle, and you need 1 handlebar for every bicycle. Well, which one is going to run out first then? You have 24 wheels, you have 10 handlebars. Which one's going to run out first? Of course, it's going to be the handlebars, right? 10 handlebars makes 10 bikes. But of course, 10 bikes only requires 20 wheels. So what's my limiting reactant, quote unquote? Well, that's going to be the handlebars. It's going to limit how many bikes I can make. When I run out of handlebars, I'm done. I don't care if I have 4 extra wheels left. I can't make a bike without handlebars. So the excess reactant then would be the wheels, right? Now, that was a really easy, simple example. You could just look at those numbers and be like, oh yeah, I know handlebars is limiting. It's not always that easy. When you're looking at a chemical equation and you're looking at numbers that aren't necessarily whole numbers like this, you're going to have to do a little bit more work with it. So again, let me show you how we can figure it out every single time without having to do it in our head. So here's our balanced equation this time, right? So this balanced equation says if I take 2 moles of Na, 2 moles of sodium, plus 1 mole of Cl2, 1 mole of chlorine, then I should be able to make 2 moles of NaCl, sodium chloride, okay? So I know what my mole ratios are. Now, let's say that I actually go and find some sodium and some chlorine to do this reaction with. And I find that I have 6.7 moles of sodium and I have 3.2 moles of chlorine. How many moles of NaCl could I actually produce from that? Now you look at those numbers and that's not necessarily easy to tell. Okay? It's not easy to tell which one I'm going to run out of first. So we have to do a little bit of math. Okay, we're going to do a little bit of a conversion here. What I want to know is which one of those am I going to run out of first? So which one's going to produce the least amount of product? So to solve this problem, I'm going to choose one of those reactants. It doesn't matter which one I choose first. I could choose the Na first. I could choose the Cl2 first. Doesn't matter, but I'm going to choose one of those reactants first, and I'm going to figure out how many moles of product of NaCl could I produce from it. All right, so let's use the 6.7 moles of Na. Right, let's use that one first, since it is the first given in our problem. So we're going to set up a mole-to-mole problem. 6.7 moles of Na is what I'm given, right? Now, I want to know how many moles of the product can I make from that. So I'm going to change it into moles of NaCl, right? So here's the deal. I need to change moles of Na into moles of NaCl. Where do I get these numbers from? You remember how we do a mole-to-mole ratio? Right? That comes from the balanced equation. Up here at the top, it says that I have 2 moles of Na and 2 moles of NaCl. So that's a 2-to-2 ratio. By the way, a 2-to-2 ratio could be reduced and written as 1-to-1. It would still give you the same answer, right? So 6.7 times 2 divided by 2 is just 6.7 again. So according to this, if I had 6.7 moles of Na and plenty of Cl2, notice we ignored the Cl2 for now. If I had plenty of Cl2, but only 6.7 moles of Na, then I should be able to make 6.7 moles of NaCl. Right? Now, we have to do the same thing with the other reactant. So now let's take the other reactant that we have up here, which is the 3.2 moles of Cl2. Let's start with that as our given. So we're going to do 2 problems here. 3.20 moles of Cl2. All right. And we're going to set up the same kind of problem. What do we want to solve with at the end? We want to solve for how much product, how much NaCl can we make from that? So I'm going to change moles of Cl2 into moles of NaCl. Where do the numbers for mole-to-mole ratio come from? That's right, comes from right back up here. Up here it tells us that I have 1 mole of Cl2 and I have 2 moles of NaCl. So I have 2 moles of NaCl for every 1 mole of Cl2. All right. Now, if we do that one, right? If we do that one, this says if I take 3.2 times 2 divided by 1. So 3.2 times 2 is 6.4, right? Okay. Now, look at what we just did. We said that if we only had sodium to begin with, right, this is how much of the product we would make. If Cl2, if chlorine is what we began with, then this is how much NaCl, how much product we would make. Well, notice the Cl2 only gets you to 6.4 moles of NaCl before you're done with it. Therefore, the Cl2 must be the limiting reactant in this case, because this is how much product it can make. Once we get to 6.4 moles of NaCl, we're going to run out of Cl2. We will never get to this number here. We'll never get there. Okay, the Cl2 is going to run out. We're going to get to 6.4 moles. We're still going to have some Na obviously left over. And so that's the key. That's how we do this kind of problem. We have to do a comparison of the 2 reactants, of the 2 givens. They gave us 2 givens. We do 2 problems, and we figure out who makes the least amount of product. Whoever makes the least amount of product is my limiting reactant. Right? So this is my limiting. And then this one right here must be my excess reactant. It's the reactant that I have plenty of, and when I actually have extra left over. Ooh, excess, there we go. Okay. Now the rest of the notes here actually show you the same thing that I just wrote out here. So I'm just going to go through them really quickly, okay? Here's a review, what we just did. Oops, let's erase this. Okay, here we go. So we did the first problem where we started with the Na. Okay. So that was the given, and then we used the mole ratio, and then we found out how much product could the Na make us. And then we did the same thing for the other reactant. So we did that with the Cl2, mole ratio, figured out how many moles of product we can make. And then we compared. Whoever makes the least amount of product, that's the limiting reactant. So Cl2 made the least amount of product. Cl2 is the limiting reactant. And the amount of product that the limiting reactant actually produces is the answer to the problem. How much NaCl could we make? We can only make 6.4 moles of it. We can't make any more than that, because once we make 6.4 moles, the Cl2 will run out and we'll be done with the reaction. All right? And that means that the other reactant, the Na in this case, must be the excess reactant. So here's a follow-up that often comes with this. Sometimes the problem then says, well, then how much excess is going to be left over from this reaction? To solve that, we have to do one more mole-to-mole problem. Okay? So what we're going to do is we're going to say, all right, we know that Cl2 is limiting. I want to know how many moles of the other reactant, the Na, would I have to use with that Cl2 to use it up. So I'm going to start with my given amount of excess, or the given amount of limiting. So the limiting was 3.2 moles of Cl2. I'm going to change moles of Cl2 into moles of Na. Where'd the 2 and 1 come from? Remember, that's from the balanced equation. So this time, this is telling me that if I had 3.2 moles of Cl2 and I use all of that up, it's going to use 6.4 moles of Na along with it. Now, how much Na did I actually start with at the beginning of this whole problem? I started with 6.7 moles of Na, right? So if I started with 6.7 moles of Na, but this problem here tells me that I'm going to use up 6.4 moles of it, how much is left over? Subtract them, right? I have 6.7. I needed to use up 6.4 of it, so I'm going to still have 0.3 moles of Na left over when this reaction is done. Okay? So, quick review, right? If they gave you the amounts of 2 reactants, they gave you 2 givens in your problem, you have to do 2 problems to figure out which one is the limiting. Whoever produces the least amount of product is your limiting reactant. Then if they ask you how much excess is left over, use the limiting reactant to solve for how many moles of the other reactant, the excess reactant, would need to be used, and then subtract it from the original amount you had, and that tells you how much you have left over. Okay? Again, these kind of problems are the kind of problems that at first seem complicated, and then you work on them a couple of times and you realize it's basically the same process over and over again. But you do have to practice them. That's why you have some of these in your homework problems to do. Okay? Now, along with this, there's one other concept that's going to be really useful to us in here, and it's called percent yield. Right? Percent yield is an idea that if we were to do a chemical reaction and we were to follow exactly what the balanced equation tells us to do, and we did it perfectly, then the balanced equation is telling us then that the maximum amount that you could actually make is what the balanced equation actually says. Right? So if it says 2 moles of Na plus 1 mole of Cl2 makes 2 moles of NaCl, if it tells you that, and I take exactly 2 moles of Na, and I take exactly 1 mole of Cl2, and I mix them together, then according to that balance equation, I should make exactly 2 moles of NaCl when I'm done. But guess what? That doesn't happen in real life. No equation, no reaction runs perfectly, right? And the problem comes from the fact that you're talking about reactions that involve collisions of atoms. Every time atoms and molecules have to collide so that they actually react together, everything has to come together perfectly. You can't control all of that. If you put a bunch of Na and Cl2 into a container and you just let them react with each other, how can you be certain that every single Na and every single Cl2 are going to bump into each other and actually, turn into NaCl? You can't. There's no way for you to control that. Therefore, there's no way that you're going to always get exactly what you're supposed to get out at the end. So we want to sometimes figure out how much compared to the maximum amount did we produce? What's the percent yield? So I don't care what chemist you are in the world, right? I don't care if you're the best chemist that ever lived. I don't care if you're that guy on Breaking Bad. I don't care who you are, okay? If you are doing a chemical reaction, you are going to produce less than what the balance equation tells you should produce. You always are, okay? So the theoretical yield is what on paper, on a balanced chemical equation, that we're supposed to be able to produce. That's called the theoretical yield. But in real life, nobody, and I mean nobody, ever produces that amount. You always produce something less than that. That's called the actual yield. And if you take the actual yield divided by the theoretical yield and you multiply by 100, you'll get your percent yield. Right? It's kind of like figuring out what your grade on a test is. The theoretical yield on the test is the maximum amount of points the test is worth. The actual yield is how many points did you get right on the test. So if you wanted to know what your grade on the test was, you take your score, you divide it by the total amount of points on the test times 100. Obviously you're always shooting for 100%. You want to get the same actual yield as theoretical yield, but you can't always do that, right? So the same thing happens for a chemical reaction. We're going to have to figure out what is the theoretical yield that I'm supposed to get, and then the actual yield is how much did you get when you really did it in real life, and you divide those two and you multiply by 100. We're going to do an example of this, okay? Here's our balanced equation. You notice it's a nice, easy balanced equation because, for one, all of the coefficients are ones. Right? So it's 1 mole of CaCO3 yields 1 mole of CaO plus 1 mole of CO2. So that makes it easy. Plus, it's also easy because there's only one reactant. Right? If there's only one reactant, hey, by the way, what type of reaction is this if it only has one reactant? Hopefully you just said decomposition, right? So this is a decomposition reaction because it only has one reactant. Anyways, since it only has one reactant, we don't have to worry about what the limiting reactant is in this case. We already know that CaCO3 is the only reactant that we have to worry about. So here's a typical percent yield problem. Right? It says, what's the percent yield of this reaction if 24.8 grams of CaCO3 is heated to give 13.1 grams of CaO? Okay. We have to identify a few things here. Remember, our equation for percent yield, right? Percent yield is actual yield over theoretical yield times 100. So I need to identify, if I want to find the percent yield, I need to identify what's the actual yield, what's the theoretical yield. Remember what those mean. Actual yield is how much did you actually make in real life? Well, you didn't actually do this, so the problem has to tell you how much you produced. So they do. They tell you how much you produce. They told you that it gives, right, it produces 13.1 grams of CaO. So you know that the actual yield here is 13.1 grams of CaO. Now we need the theoretical yield. And you might think, oh, I have this other number here. I can just put that at the bottom. But no, it's not that simple. Because notice, this is CaCO3. This is my reactant. This is how much I started with of the reactant. I want to know what's the percent yield of this product, right? You can only find a percent yield of a product. You only yield products. So the other number that they gave us there, the 24.8 grams of CaCO3, is only going to be useful if we turn it into CaO. So we do have a problem to do here. To find the theoretical yield, we're going to have to use the 24.8 grams of CaCO3 to find how many grams of CaO theoretically we could produce, right? Once we know that number, we can plug it into our equation over here on the side, and we can figure out what our final answer is. Okay, so our job is to find the theoretical yield of CaO. So we have to do a mass-to-mass problem. Our given is 24.8 grams of CaCO3. So let's write that down. 24.8 grams of CaCO3. All right. Let's write down what we're trying to find. We just decided we needed to find grams of CaO, right? Because that's what we needed here for our theoretical yield. So I'm going to go from grams of CaCO3 to grams of CaO. Well, we've done this before. This is called a mass-to-mass problem. Mass-to-mass problems are always 3 steps long. So I want you to pause right here, and I want you on your paper to try filling this in. We've already done some problems like this, so it's good practice for you to try again and make sure you can fill this in. So pause here, fill it in using your periodic table and your calculator, and then I'll show you what the answer here is in just a moment. Okay, hopefully you've already tried to do this. Again, trying it, even if you're wrong, is always better than just staring at my answer on the screen. Always better, I promise you. So let's go through this. My given was grams of CaCO3. I always have to put that unit on the bottom of my first conversion factor, always. So if this is grams CaCO3, this better be grams CaCO3. What do I always change the unit in at first? I always need my units to be in moles. So my first conversion factor always needs to go to moles of that substance. Now, once you know what the top of this conversion factor is, it has to match what goes on the bottom of the next one. So if I had moles of CaCO3 on the top, I better have moles of CaCO3 on the bottom of the next conversion factor. What goes on the top here? Well, this is my mole-to-mole ratio. This is where I go to moles of the other substance. What's the other substance? It's CaO. So CaO needs to be written on the top here. And finally, if I know moles of CaO is on the top of this conversion factor, it better match what's on the bottom of the next one. Remember, these always have to match up. And then I can finally get to what I'm looking for, which is grams of CaO. So before we fill in any other numbers here, let's just make sure this works. I started with grams of CaCO3, which cancels with grams of CaCO3. Then I went to moles of CaCO3, which cancels with moles of CaCO3. Then I went to moles of CaO, which cancels with moles of CaO. And I finally ended with grams of CaO, which matches my answer, which is grams of CaO. Now, let's fill in the numbers. Remember, this one is always 1, this one is always 1, no matter what. Every single problem you ever do in your entire life like this will always have 1s there. Where do the grams come from? The grams come from the periodic table. So that means you had to go and look up Ca and C and 3 O's and put that here. And then you had to look up Ca and O and add those up and put that here. And finally, what goes here in the middle, the mole to mole ratio? Well, that comes from our balanced equation. How many CaCO3s were in my balanced equation? There was 1. How many CaOs were in the balanced equation up there? Well, it was 1. So that part was really easy. So let me erase this chicken scratch. And let's put up what the final answer looks like. Here's the final answer. Again, where's the 100.1 and 56.1 come from? That comes from the periodic table. I added up the Ca, the C, and 3 O's, or I added up the Ca and the O. That's where those numbers came from. Any numbers that are on the top, I multiply by. Any numbers that are on the bottom, I divide by. And my final answer comes out to be 13.9. Don't forget, right? Don't forget. This is 3 significant figures at the beginning. This is 3 significant figures then at the end. It has to match. Now, we did all that. That is not our final answer. If you remember, the final answer was, what's the percent yield? What we just figured out is the theoretical yield. Anytime you do a problem, right, you're doing the theoretical, according to the balanced equation, if everything went perfectly, yield. So that means the final thing we need to do is calculate the percent yield. Percent yield is actual divided by theoretical times 100. Well, remember the actual from up above here? It was 13.1 grams of CaO. But the theoretical we just figured out was 13.9 grams of CaO. So we only produced 13.1. We were supposed to produce 13.9. So what percent is that? That's 94.2%. That is the percent yield. Right? That's how much we produced compared to what we should have produced if everything went perfectly. All right? So this is the setup for doing a percent yield problem. The only difference is, what if we wanted to do a problem in moles instead of grams? We could have shortened this and done just a mole-to-mole problem if they wanted us to find it in moles instead of grams. Most of the time, though, it will be in grams. All right. Again, this is the end of chapter 12. If you have any problems with this, if you're confused about anything, you need to let me know. Normally, I'd be able to walk around and help you guys in class. I really would love to be able to do that, but unfortunately, we just can't do that right now. So I need input from you guys. What is confusing you, right? You can also use the book example problems. They work out some problems for you also. So if you need other ones to look at and see how they do it. There are obviously some good YouTubes out there about stoichiometry and how to do stoichiometry problems. Or again, ask me, right? Email me, message me, whatever, and let me know. Okay? All right. Work on your homework problems for this. And remember, next week we're going to end up doing a lab, and then we're going to be doing the test on this. Chapter 10 and Chapter 12 are on the test. So think about that ahead of time. All right.